fifth part of our graphics series. In this particular element, we're going to have a look at the notion of animation. In particular, the notion of an animation of a sequence of images. I highlight that because there's actually different ways in which we can animate objects within games. And obviously animation is important because it conveys movement or motion of our objects. Depending on how you think about this, certainly within 3D games, the more common form of animation is where we have a model and we rotate and move the different elements of that model over time and then animate it in that particular way. We can do something similar within 2D games, but the other option we have within 2D games, which also applies to 3D games as well, is the idea of taking a sequence of images and playing back that sequence of images over time at sufficient frequency that they are perceived by the viewer as a continuous animation, an animated sequence. So that's where we're going to have a look at how we can accomplish this within a simple implementation. So image sequences. An image sequence is simply a series of images displayed one after the other. Fair enough. And if we do it fast enough, then we will perceive it. So the brain will interpret that then as continuous motion. So that raises or poses a question of, well, how fast is fast enough? And you might want to think about, if you do want to play back a series of images and you want for those images to appear to the viewer to be continuous, that they perceive them then as an animated instance of some object as opposed to a number of discrete pictures, how fast do we need to play them back? So a couple of options down at the bottom. Is it 50 frames a second, 30 frames a second? That's typical for how the frame rate of mini games nowadays. Is it 10 frames? Is it 5 frames? Way of answering this, we think about TV, and it differs depending on the region, difference depending on the technology, but there it can be 24, 30 frames a second. Some of the high definition stuff for the movies getting on to nearly 50 frames a second. So we know that if we play it back at arguably 25, that is good enough to be perceived as smooth, continuous motion. But it's actually any lower than that. Well, we can do it. So here we have an example of 6 separate images. And if we play back those images, we'll get the appearance of a ball bouncing. And if I'm playing them back at 2 frames a second, you can see them here, that doesn't appear to be continuous motion. It's discrete images being displayed. And we look at that and okay, you can sort of imagine it being the bouncing ball, but we don't perceive it as a clearly bouncing ball. So 2 frames a second, not good enough. If we were to go to 10 frames a second, it's not a particularly large amount, but at 10 frames a second, it looks reasonable. We can sort of look at it and go, yeah, that's a bouncing ball. It's broadly acceptable as an animation. And in fact, long time ago, whenever cartoons actually were drawn by hand, I know on that notion, each individual frame as opposed to done on the computer, it was common then that typical animation would have had 12 hand-drawn frames per second. And you can see an example there of playing back an image of a horse running, where at 12 frames it looks reasonable. Reasonable in the sense that I suppose we are wired up. If we see a series of images where we think that they're interconnected, we will perceive them then as being interconnected. And at 10, 12 frames a second, that's good enough for making it believable. So that's handy then. It means if we're doing 2D games and we're looking at animated sequences, we don't need a vast number of different frames within our animation to be able to actually use them. So we know we can do this then. If you do a Google Images, or you get some of the resource CDs, you'll find lots of examples of animated images out there. They'll come in different formats, and some of the formats may be that we will have individual frames in individual files. And this is important because inside the game, we're going to have a look at a little fragment of code which we'll create to enable us to play back these to give the appearance. But arguably, we're going to have to do more work at loading the things into the game. This will then depend upon the file structure, how they're located on disk. And sometimes it'll be easy to load it in. Sometimes we'll have to do a little bit more work, depending on just where and how the source images are located. But one option, as you can see here, is a series of separate files where we have one frame of the animation per file. Fair enough. Another option is known as an image strip. You can see it's down at the bottom, where we have a total of 10 frames. Yeah, 10 frames in this case, showing the frames of an explosion effect. So there it is, one file, one image, but inside that we have basically concatenated together all of the different frames of the animation. So that actually makes it easier. It means then we have one thing to load in, and when we're playing that back, effectively what we're doing is we're not drawing out the whole image, we are drawing out a specific rectangular region within that image that corresponds to the frame that we're drawing out at that point in time. So that's one load, but then it's a question of how do you appropriately build the rectangles. In the case of this one here, if you look at it, you'll notice that each of the frames of the animation have the same width. Now this is a horizontal, this is a vertical image strip, but fair enough, so it's the same width for each of the frames. So the first frame of the animation, even though it's as small as just the explosion starting, has the same width as one of the frames in the middle of the animation. Now, consequences to this, swings and roundabouts, it means that the image size actually is a bit bigger than it needs to be, but it's very easy then to work out a rectangular region. If I'm on the fourth frame of the animation, I can say what's the width of it, divide that by the number of frames, then create a rectangle around the fourth one in. The other option, sometimes you'll find this when you're downloading image strips from online sources, is that it will have a variable frame width, that there is minimal gaps put between them. So that means that the width of the first frame is probably going to be different than the width of the second frame, it's probably going to be different than the width of the third frame. That makes it a wee bit more complicated because other than loading in the image in the first place, we also then have to have access to some other piece of information. It could be in a table that tells us how wide or high or the size of each of the frames. And we then use that to form the rectangular regions. Third one you might find is a notion of just an image sheet, where you can have rows and columns of different frames within it. So it's an extenuation of the notion of the image strip into one. So there's another example of explosion where, as opposed to one long image strip, which arguably would have been more easy to handle, it's split into what's that, a 5x3 matrix. And again, in this case, all of the frames of the animation have the same width and height, which makes it easier to extract. But some of the stuff you'll find online may have variable widths and heights between them. Little aside shown here, for best performance, all images should be stored on an image sheet with all animations using that sheet rendered together. And this comes into how graphics cards like to work. Generally, if you have one large image with all of the information together and you're drawing all of the objects that use that animation, it means that you only have to have one image available up on the graphics card, and then you're just drawing out different regions from it. That's very, very fast. If you have to keep swapping the images that are drawn, so for example, if it's one separate image per frame, then that puts a greater burden on the GPU because you're telling it, okay, we're going to draw from this image, then we're going to draw from a completely separate image which has to be loaded in and swapped around and things like that. Overall, I would suggest that if you have all other things being equal, favor image strips which have the same width or height for each of the frames. That's going to make the coding very much more straightforward in terms of the amount of processing that has to be done loading it in. If you do have something that you really want to use which has variable widths, then quite often I'm afraid is actually sitting down with a piece of pen and paper, working out the region for each of the different frames, and then having a separate data structure which loads in that data so you know the region you want to extract to draw a particular frame. Okay, So let's assume that we have loaded in our image data that we want to do. Now we want to have a little fragment of code that will enable us to play it back at a sufficient speed so that it appears to be a continuous animation. Now, we're talking about game objects here. So game objects, we have the notion that we update the object and then we draw or render the object. And we want to take our idea of an animation, which fundamentally is a visual thing, and to integrate it into that model. So in this case, it's important that when we are updating the object, what we actually will do is to work out which frame of the animation we ought to be displaying at this particular point in time. So that will be a decision we will do in the update phase. When we're drawing it, we will simply say, well, which frame have we picked? Let's draw that frame out. So there we have separated the two entities. And because the game can evolve, we could pause the game, the playback of the game. It's important then that anything to do with selecting the frame of the animation is something we have within the update phase. I'm going to give you an example of one implementation of how we could do this. Now, it is only one. You can have as many different implementations as you want, but it'll illustrate some of the aspects as to how we can do this. So we're going to assume here, you can see over on the right-hand side, that we have an array of images. Now, if it was an image strip, it would be an array of rectangles into that particular image strip. I'm just assuming here's an array of images, just for sake of simplicity. Beyond this, we also have the play count. Now, the play count, we're going to use this as a variable that tells us how many times we're going to be playing back something. So if you think about it, some animations are play once. So if I have a door and I have a door open animation, I only want to sort of, okay, open the door, play that animation, then stop. Some other animations, for example, say it was a flickering flame, I may want to keep playing that continuously. I don't want to play it once or twice. I just want to keep on doing it until I don't need to do it at all. So we need a mechanism then whereby to indicate when we're playing back something, just how frequently we're playing it back. And the most common ones are you either play it once or you keep on looping it. But this is where play count comes in. So number of times to play the animation. If it's -1, we will interpret that as meaning play it continuously. If it's 0, we will interpret that as meaning pause the animation. The animation is not currently playing. So this one variable unpacks the notion that sometimes we want to play back a specific number of times, sometimes we'll not be playing it back, and sometimes we'll be continuously looping it. So our -1, 0, 1 positive integer have those different interpretations. Home frame then. So here we have the idea that these are for the sequences which sometimes may not be animated. So I might have my closed door. The other frames in the animation are the images of opening up. And if I'm not playing it, then the default frame of the animation that I pick, well, you could say it's just going to be the first one. In this case here, we're saying we have a separate home frame that tells us the frame of the animation that we default to when we're not drawing it. And I suppose most often that will be the first frame in the animation, but not necessarily. Current frame then is the frame that we will be displaying at this particular point in time. So the animation may be playing, it may not be playing, doesn't matter, but current frame will determine, it'll be worked out, and it'll be the one that we will actually then draw. Animation period. So this, a couple of different ways you can do this in different implementations. Some implementations will store the number of milliseconds for each individual frame. That's fine. The particular interpretation I'm using here is it is the number of milliseconds for the complete animation to conclude. So if this was the door opening, then it would be how many milliseconds does it take for that whole animation to play. If it was a flickering torch, then it would be, well, I don't know, it depends on what's in the animation, how much time per flicker of that torch. And the final thing we have is a start time. So animation occurs over time. We need to have a point of reference whereby we can measure how much time has elapsed from that, or starting time, and then use that to determine, well, what is the right frame of the animation that we should be using. That's our start time. So that's the variables that we're going to have within our algorithm. By way of update and draw, you can sort of see the things here. So update, we work out the current frame. Draw, it doesn't matter what it is. I mean, there we're just simply drawing out the current frame. So that's a particular implementation. And again, it'll be an object that'll be using that animation. So you want to draw out the animation at wherever the object is or relative to the object. Okay, so the interesting bit then is this algorithm. So the whole ability to play it back fits quite comfortably onto a single screen, so there's not a huge amount to it. There's a few things in this again which are more housekeeping as well. So the actual animation code is really fits into line 12 to 20. But we'll go through this here. So lines 3 to 5 is the first thing we want to have a look at. Line 3, we arrive into this, we get the current time. So animation is time based. So this here says, okay, well, what time is it? Give me the current time. So we need that. Line 4 and line 5. So start time. Start time was the entity, the thing that tells us, okay, when did we start playing back the animation? Now, there's two cases here. One case is we have actually started playing back the animation and we have a real start time. The other case is that we've come into this method and we are just about to start playback of the animation. Now, there's different ways this could have been done. This particular implementation assumes that if start time has a value of -1, it is used to signify that actually we haven't started it, but on this particular call, we are just going to start it. So start time, if it has a value of -1, it's been set somewhere else. This has been our trigger to start playback of that animation. And on line 5, what we do then is that we actually record the start time. In subsequent calls, our start time will have an actual value, so then the animation has commenced. So again, line 4 and 5 is really there just to deal with that particular situation about how do we indicate that we have commenced playback. And there's different ways of doing it, but it's been put in this implementation just to indicate or to highlight that there's going to have to be stored somewhere. Line 7 to 10 then deals with the other extreme. So if you're not starting it, we may also want to finish it. And this is the idea that the animation can come to an end. We may be playing it twice or once or whatever. And then how do we detect that we got to the end and what do we do in that particular circumstance? So if play count's greater than 0, line 7 says, okay, are we actually playing it? Line 8, which splits onto line 9, works out, okay, current time minus start time. So this is asking how much has elapsed, how much time has elapsed since we started playback. And if the total amount of time is greater than our animation period times the number of times we're playing it back. So this means if we're playing it once, then it's just 1 times the animation period, or playing it twice, 2 times the animation period. But if that elapsed time is greater than the duration we're expecting it to be, then we set our play count equal to 0. And that's simply our way of indicating that we have completed, we've concluded our overall playback of the animation. Again, different ways of implementing this. You might, for example, always want to make sure that the final frame of the animation is displayed before you then actually do officially go set your play count to 0. Line 12 then down to the rest. This is where I suppose we actually deal with the normal default case. So if play count's equal to 0, this is line 12. So in other words, we're not playing it. Either we've stopped or we've yet to commence the thing. The current frame, the frame we're going to be displaying, is simply equal to our home frame, whatever one we defined. Line 14, the else, it'll be true if the play count is not equal to 0. And we can assume here, or rather we would assume it has a positive value at this point. So line 15, it works out how far we actually are into the current animation period. So what we do here, so it's current time minus start time, so we've worked this out. Again, this is how much has elapsed since we commenced playback. We're taking that the modulus of the animation period. Now we do that because this algorithm has been set up to enable us maybe to play back the animation 3 times. So we want to work out how far into the current playback period we are. I'm taking the modulus then. We'll make sure we're always looking at a value that is relative to one particular animation, the current one. So this tells us how far we're into it that we are. Line 17 then works out which frame corresponds to that. So you can see here that the time into the animation period, multiply that by the number of images we have, divide it by the animation period. So for example, if animation periods, if our door open animation takes 1000 milliseconds, and we are 400 milliseconds into it, and we have 10 images available, then effectively, 400 divided by 1000 is going to, well, using integers here, that's why I do the multiplication, but effectively that's 40% into the animation period, and we will take the animation frame that's 40% through our available array of frames. So fairly straightforward. And again, that determines the frame we want to display. Line 21 is where we return with whatever frame it is we want to display. So either going to be our home frame or the one that we have selected based on our location within the animation. And that's it. So one reasonably simple algorithm enables us to select the appropriate frame to play back as part of that animation. Takeaways from this: there's not really much to it. You can see that from the algorithm. The idea of playing back a sequence of images at a certain frequency is actually quite straightforward. The more difficult things is just making sure that all of the things are aligned, and sometimes it can be more complicated if you have multiple animations and you're swapping and changing between them. And the other thing here is just to mention that depending on the actual format that you load your data in, and if it's nicely populated and sort of fixed with image strips, or if it's not, sometimes you might actually have to do a reasonable amount of work massaging or manipulating or extracting the data to pass through your animation algorithms. Now, that's all we want to have a look at this one. The next in our graphics series, we're going to go on to have a look at the notion of image ribbons.